Hi guys, hope all of us are doing great. I'd like to welcome each and every one of us to my channel, and I'd like to request members to kindly go to YouTube and search Ernest Sciences and Mathematics TV channel. Subscribe, engage us on the comment section, and invite more for members to come and join us so that we can be contributing to various topics that we have done in mathematics, physics, chemistry, and biology, and also assist one another in problem solving in these specific areas that I've mentioned. So today we're going to look at the Gaussian services, and this is of course an additional concept that we're going to look into under the concept of electricity and magnetism. And earlier on we had looked at the concept of the Gauss law and tried to establish the relationship that exists between the electric field and the charges that of course are found in this specific region in space that we had referred to as an electric field. And therefore, in our last discussion, we had also looked at the concept of electric flux, which we had given in terms of a formula. And today, this is going to assist us, of course, in trying to define what basically we refer to as a Gaussian service from a geometrical perspective. In our last discussion, we had said that we can be able to represent this electric flux if we consider a flat surface and some, of course, of area A, and we are considering electric fields that are emanating from this surface, which are normal to the surface area, of course, in this particular case. And we said that these electric fields are vector fields, which are going to be experienced in this specific case. And therefore, we argued that we can be able to represent the electric field lines that are emanating from this, of course, and give it as a relationship between the area and the electric field that we had considered for a general formula for representing an electric flux, which basically we defined as a number of electric field lines which are passing in a given area over a specific time. So in this case, today we're going to look at which specific areas are being referred to as Gauss services, and what are the implications of Gauss services on some different representations that we had given in our discussion on the electric flux and the Gauss law in our last video. So I'm going to start this one by giving an illustration, which is going to give us a figurative way in which we can be able to represent this specific concept of the Gaussian services that is going to be heavily employed in, of course, in trying to do some calculations on the concept of electric fields, especially now that we're going to consider areas of a gravitational field. And basically, we've talked about this specific concept in some of our videos that we have already discussed. So I'm going also to talk about the magnetic field and the electric field that I've mentioned, of course, in our introductory part of this specific video. So we're going to establish the relationship between these three and what we refer to as the Gaussian service. And as we had mentioned, basically this consists of a range of what we refer to as vector fields, which have magnitude and direction. So our illustration is going to create an emphasis on this, specifically on the direction and basically the magnitude of these electric, magnetic, and gravitational fields respectively. So my representation is going to tackle on these specific areas and how we can be able to conclude whether that service is a Gaussian service and what are some of the conditions which are being attached to this specific concept of Gaussian services. Now, if we are going to consider the illustrations that I've given on the board, of course, I've given some details which I'm basically going to explain what they basically consist and what are their implications from the definition of our Gauss law. Now, in this case, the first one is a spherical shape illustration. The second one is a cylindrical, and the third one is a two-dimensional illustration of a circle. But of course, we are going to use this one in trying to explain what basically it implies and the relationship between these three and one insofar as two-dimensional and three-dimensional are concerned. So this is going to give us a figurative way of trying to explain the concept of Gaussian services. And of course, from the definition, the concept of a service from a topological view is a two-dimensional, of course, illustration, which is going to give what we call a set of points which have got a length and breadth, but have got no thickness. So this basically refers to the concept of a two-dimension. And if we were to look at from the Cartesian coordinates, we can be able to perceive a surface as two-dimensional points in space, which of course are going to be having the breadth and length but no thickness. So in that case, that forms just a rough illustration of what basically the concept of a surface is. Now for a Gaussian surface, therefore, it's going to be a surface in 3 dimension. Now in our case, this is going to imply a third concept. For these Cartesian coordinates, we can be able to then give this specific illustration for x1 and z. So therefore, a Gaussian surface is a surface in a 3 dimension which is enclosed and where the flux of a vector field is determined. So this is an enclosed surface in the first case, an enclosed surface, and then we are going to have that, see that this surface is of course symmetrical. I mentioned this specific concept in the first case on the Gaussian law. So this is going to be a symmetrical surface, and then lastly we're going to see that this surface is imaginary. And therefore, the implication of Gauss' law is going to be very fundamental in trying to establish the electric fields or the electric flux of surfaces, especially which have got this specific sense of asymmetry. That is why I've given the illustration for these spherical, cylindrical surfaces, so that they can assist us geometrically to try to calculate the concept of electric flux. So therefore, I'm trying to look them from that specific perspective. Therefore, the Gaussian surfaces encompasses a special class of surfaces which are enclosed, as I've said, and of course are going to contain a particular volume in space, and which are of course symmetrical, as I've said. And in trying to look at this, of course, we're going to consider the aspects of spheres and cylinders in this particular case. But later on, we're going to see that Gaussian surfaces can also be considered for these specific surfaces for electrical charges which are either enclosed or where charges are not enclosed. In this specific case, for illustration number 2, I've given an enclosed charge, and also for 1, an enclosed charge for positive. We are given characteristics of field lines, which of course I'm going to give using the third illustration. So therefore, this I field electric field lines which are emanating from that positive charge. So therefore, this specific surface is what we refer to as a Gaussian surface. And for this cylindrical part, and also for this, of course, we're going to use these ones are appearing in 3-dimension space. So therefore, they are going to be Gaussian surfaces. For the Gaussian spherical surfaces, Gaussian cylindrical surfaces, respectively. And for this, of course, surfaces, we are going to note that the unit normal, which I've illustrated using this M with the node of the heart over there. Therefore, the unit normal to the, of course, for all the literal elements for the areas of dA that I've given in this specific part for the, of course, these specific surfaces. And for the second illustration, I've given this unity area for this specific part, this one and this one, which are illustrating the sections of the curved surfaces. So we had given the formula for finding electric flux for curved surfaces, or for electric flux for Gaussian surfaces as phi, which was the summation of these specific surfaces for an enclosed. We say that this is going to be given as a small o that is, of course, embedded on this specific sign, and therefore this is going to be given as E dA, which basically is a summation of these units, small unit elements, which are going to assist us find the flux for these surfaces. Now, essence for us is to try and look out for this specific characteristic for various aspects of the Gaussian surfaces, and this, of course, is going to assist us in trying to find the electric fields and the charges of different areas that we're going to consider, especially for the symmetrical aspects of 3-dimensional spaces for spherical and cylindrical parts, which of course are going to explain the concept of Gaussian law that we had discussed in our first video. Now, essence for us to remember is that the Gaussian surfaces basically are 3-dimensional enclosed surfaces which are going to be containing this flux of vector fields, which of course I've explained for three examples for gravitational, magnetic, and electrical field respectively. This is going to consider the aspects of symmetry, as I've said, because basically for symmetrical aspects, they are going to consist of what we call even charge distribution or uniform charge distribution. Therefore, from that one, we can be able to calculate, of course, what we refer to as electric fields and other fields associated, which I've mentioned for gravitational or magnetic fields. And this, of course, is going to assist us in trying to find out how these Gaussian services can be of importance to us, for us insofar as electric flux and other related topics are concerned. And before I forget, of course, we're going to mention this. I've just given these services, but we're going to note that the unit normal to these specific services, of course, the elements dA that I've given are going to point outwards. For the first case, as I've illustrated, for this, the second and the third one, as I've given this one. And this specific special notation that I've given for these particular services, where we are going to have a circle that is superimposed on this specific summation sign, then therefore it's going to represent the service integral over closed services for Gaussian services, which basically I've said going to consisting of basically services that are symmetrical. And thus, of course, we can be able to represent generally the Gaussian service, or rather the Gaussian services electric flux using this specific sign. So in our subsequent discussion, we're going to consider the Gaussian services for enclosed charges and other areas that we're going to look into, which are related to this, as I've already mentioned. So catch us in our next video, especially on the concept of capacitance that we're going to calculate its magnitude and other aspects of for Gaussian services respectively. So that is it for now, guys. Catch us in our next video. Kindly check on the link in the description box for various related videos, so that we can have a comprehensive understanding of the Gaussian law, the electric flux, and the Gaussian services that we have discussed in this specific video. So bye, God bless you.